Yeah, let's get started. Good day, everybody. Thank you for coming to this presentation, the webinar for one of our core modeling theme, which is advances in spatial meteorological forcing. This team is led by Professor Julie Theroux. She will present on behalf of the team on the advances that they have made over the past year on the meteorological forcing in the core modeling theme. I would like to take some time to introduce Professor Theroux. Julie Theroux is a professor in the Department of Earth and Atmospheric Sciences at University of Quebec, Montreal. She is basically interested in extreme events and also the events which are close to phase change at a temperature of 0, which is quite important. She is leading this important team for the core modeling team, which is basically the engine and the driver of all our hydrological models. So we are dependent on the good quality data that they produce for us, for our modeling. Basically, the output from the team is that historic data, real-time forecast and future scenarios, evaluation of the quality of each of those data, and possibly bias correcting them and preparing them for the use in the hydrological modeling. I think Julie will talk about it more in detail at the end, and I'd like to welcome you on behalf of the core modeling team to this presentation. Al Petroniro, Martin Clark, Joy Mitigiani, and myself, Sherman Qarari. I hope you enjoy the presentation. Julie, the floor is yours, please.
Thank you very much for the introduction. Bonjour tout le monde, and thank you very much for attending, also taking the time to attend this webinar. So I'm happy to share with you today some of our advancement in the past year in the spatial meteorological forcing data team. So today I will be presenting, this is gonna work. So I will be presenting the work that has been done by the team. So I will go over all the projects, and the team includes 5 faculty members from UQAM, University of Saskatchewan, and University of Calgary, and also 6 HQPs, PDF in general, but also PG student, and also many collaborators from NCAR, Environment Canada, and also from UQAM. The goal of the spatial meteorological forcing, I will close this. Okay, the goal of the spatial meteorological forcing data team is to produce surface meteorological data to study past and future climate. And this also includes study of extremes and also forcing data for hydrological model. And what is developed in this team fills in the gap in the existing data set that are already available across Canada, North America, and also globally. So I tried to summarize this in 2 different parts, and this is summarizing what I will present today, and I will give another overview of the research activities that is conducted in this team. In particular, the first part is to go over the observational data set and the existing model product, how the data sets are manipulated to develop new data sets, the evaluation of existing data set, and also the evaluation and the bias correction of, for example, here, the model product is CNIP6. The second part, which is also a big part of this team, is the production of regional climate simulations. In particular, you're probably aware of the WRF bonus 1 and 2 simulations in Western Canada, and also some activities using the Canadian, the Global Environmental Multiscale model. So I try to represent this in a different manner here by summarizing it, because some of you are interested into historical data or climate data. So in blue, the historical data, so those from satellite and station, but also the GEM simulations that we're planning to do. And then in terms of studying the future climate, there are the climate projections that will be available with the CONUS 2, and that is available through CMIP 6. And then the one in purple, I didn't know which color to put, because it's providing historical data, but also information about what will happen in a warmer environment, so the pseudo-global warming. So there's 3 types of data set here. So in the first part, I will start with the first part where the work is done on the observational data set and the existing model product. And the first project I'd like to present you is what Gaochen Tang has been doing in collaboration with Martin Clark, Simon Papalescu, and John Pomeroy over North America and also globally. So last year, I presented to you a few data sets that were already done and that is already available. And then in the past year, Gaochen was very productive and then produced another one, a serially completed for the globe, so for the planet Earth. And also compared to the first 2 data sets, it's available for a longer time period. And also some of the variables are available for hourly. And also compared to the previous data set, the dew point temperature is also used. So this is a detailed description is available in a paper in the Journal of Climate. And so now the second step here is to develop an ensemble data set, but for the planet Earth. So the motivation for this is that there's some limitations in measurements and models. The ground station, it's point scale, limited coverage and measurement errors, as we know. Remote sensing, there's also limited coverage, but also it's available for a short time period. And there's some, as we know, approximation and sometimes issues with atmospheric models in terms of the observations available for evaluation, the resolution used, and the parameterization. So the idea in the ensemble Earth here is to create a gridded data set, and numerous regional and global deterministic data sets are being developed. And there's also a lot of the data set have some uncertainties, but only a few data set provide some uncertainty estimate and uncertainty-based ensemble estimation. And this is what Gaochen is doing in this project. So the framework of the EM Earth is summarized on this image where the raw data are taken, then the serially completed Earth is taken, and then some, and it's combined with RL5, and some statistics is done to create 25 members and therefore the database. The variable used is the precipitation, the mean temperature, daily temperature, and dew point temperature, available at different frequency and also at 0.1 degree. So there's a deterministic estimate and also a probabilistic estimate, as I said, with 25 members. The input station here, just as an example, we can see on this diagram the number of stations available globally, with a lot of stations over North America here, as we can see, and a little bit less station over Africa. And then this is an example of the variation with time of each of the variables. So this data set is used, as I said, as part of the production of this EM Earth ensemble database. The variables are this, as I said before, and various methods are used to develop this credit database. This is an example of the results. The EM Earth ensemble estimate can be used to characterize the uncertainty in hydrological modeling, particularly in basins where where ground observation are scarce. And then you can see here in January 1950, the 25 members that they're simulated, and this gives you the number of millimeter per day. And here give you different scenarios using the SUMA model and the Mizu-Roth runoff model for the 25 members. So Gauchen has submitted the publication and then waiting for the revision. And then the next project is evaluating satellite data set for Western Canada. So as a little bit of background here is that we are conducting some GEM simulations that I'll present you later. Then we're looking for data to evaluate the simulation. And then we thought that using the satellite data would be a good option. So it provides a product that is a relatively high temporal resolution at 30 minutes, and also it's a gridded product for, well, a limited time, but for 6 years, I think, that we use. And the goal here is just to use the 4 satellite database product and to compare it to the ground observations across Western Canada. So Manoj Nambiar is working on this, is working on comparing it basically from 2014 to 2019. And then we use the geographical regions that are defined by an RCAP, the climatic zones. And there's 122 ECCC stations that are available for that time period. And those are the 4 satellite products. So we aggregated them for over a frequency of 3 hours. And the result that I will show you will be using a Taylor diagram. And I thought of using a slide to present it to you in case you are not familiar with it, or in case you are familiar, and then you need a reminder, because there's a lot of information, I think, on a Taylor diagram. So basically, the star is the reference here. So we want the point to be closer to the star. On this axis, there's the correlation from 0 to 1. And on this axis, it's the standard deviation. Those circles, we can see these are the RMSE, the root mean square error. So I chose 3 different geographical stations to show to you. For example, that the NSWAP and the GSMAP provides the best estimate for all those 3 regions where the correlation is around 0.5, and then the standard deviation is also really good compared to the reference, which are the stations, and also a lower RMSE for all cases. I merge at the highest RMSE, but comparable correlation with others. So in summary, those 2 satellite products perform better than iMerge and CMORPH. And we think that it's basically because they also use the precipitation gauge to create this product. So this is why also that it compares better to the gauges. So those satellite products will be used to evaluate the GEM simulations, where I will show in part 2 of this presentation. So in the part 1, where we use some existing database, there's also some work that is done by Chandra Rajulapati, PDF with Simon Papalexiou, and she works with the future climate scenarios using CMIP6. So this is a bias correcting CMIP6 projection project, where they use maximum temperature and minimum temperature between 2021 and 2100. Many simulations are used, and different socioeconomic pathways as well are used from the 30 CMIP6 model. And then we see the link with other projects where they use the EM-DNA to do the bias correction. We can see here on this figure the annual mean temperature variation from 1980 to the end of the century and the variation of temperature for the different socioeconomic pathways for Canada. We can see a range of annual temperature for the different pathways. So what they have done is they assess the changes in temperature in urban areas across Canada, where they chose 18 cities with population with more than 200,000 people. And then the different cities behave differently. So in red, I just highlighted in red the region in the prairies in Saskatoon, where the increase in temperature, the trend is lower than the trend, for example, observed over Montreal, where it seems to be warming a lot. They also extend this project to the globe, where here you can see the different change in the temperature anomaly or the evolution in the temperature anomaly with time across the globe on this panel, then North America, Europe, Africa, Australia, and Asia. The temperature anomaly increased up to 7.5 degrees on average when using the highest scenario. The cities in North America and Asia and Northern North America are warming at higher rate compared to other regions. About 27% of the cities maintain an anomaly level of 1.5 degrees, which is the most optimistic scenario. So in summary, we see well the link here within this team that the product developed by Gao Chen is used to bias correct the CMIC6. We see that the temperature trend between the 18 cities study are different. And also there's some activities done over the globe, and I invite you to contact Chandra and Simon if you have additional questions or interested in those results. So this ends the part one of the webinar today. And then I will go now into part two. I think I'm speaking a bit fast, so I'll try to slow down. So the part two, it's the production about the regional climate modeling. And I think that many of you are interested to use, in particular, the CONUS 2 simulations. So I will take more time to describe to you the CONUS 2 simulations and also to present to you some preliminary results that Yang Ping's group has provided to me for this webinar. So first of all, I wanted to start with the GEM simulation. That's a much smaller effort than the CONUS simulations, as this is done by Manoj Nambiar, which is a PDF at UQAM. And we want to do some simulation over a more smaller domain. And then, so we're working on getting the best configuration to be able to simulate accurately, or the most accurately as possible, snowpack during the cool season and the change in precipitation phase and intensity. So what we're using is the GEM model version 5 that is installed on Compute Canada. So we run on Beluga, and this version has been currently adapted to run into regional climate mode, and it's going to be the 6th version of the Canadian regional climate model. So the model configuration for those simulations is we need to start with a bigger domain, and then we start with a bigger domain, and then we nest to a 3-kilometer resolution domain. We would like to eventually do a 1-kilometer resolution simulation to capture well the Canadian Rockies. We decide to focus on a 2-month period, a period where we have detailed observation at very high frequency. during the storms and precipitation across the continental divide experiment that was from the end of April to the end of June 2019. So the experiment was in this area, so the domain chosen well covered this domain area. So we use the predicted particle properties to as the microphysics scheme. This is a newly available scheme into GEM, where there's only one ice category that predicts snow, ice crystals, and the degree of rhyming of particles. We use model output of 1 hour. And then we try to find the best way to do the simulations by doing a 2 steps or 3 steps simulation, starting with ERA directly to 3 kilometer, or starting with ERA at around 3 kilometer, simulating at 12 kilometer and then 3 kilometer. So this is possible because of other projects that also work with this regional climate model, where we try to find the best configuration for Eastern Canada, and we're trying to merge the effort here. So a series of simulations were conducted during this 2-month period. So I would say that this is, I call it experiment 1, but maybe it's more like the control, where we use 30 to 3, so the simplest approach using ISBA. And then we change the crop into ISBA. So we added another option. And then we also try with spectral nudging. And then we try to do an intermediate simulation, 30 to 12 to 3 with ISBA. And then the last option here is done with class. So we have hoped to be able to use class in those simulations. And also one thing that is new is that we use the microphysics at 12 kilometer, and then we're forcing the 3 kilometer with also the microphysics, so the clouds and precipitation aloft at the boundaries. And so that that improves significantly the simulations, because it's starting at closer to reality. So this is an example of some results. So when we look at a point, so basically this is the map. So we have the Canadian Rockies here, a station here at lower elevation, one at higher elevation, power line at around 2 kilometers above sea level, and then Nipika, which is a station on the other side of the divide, on the west side in BC. And then we're trying to see when we use the closest point, which simulation is better. But it is really hard to tell, because we see a lot of differences. In black, there's a SPADE data at both locations. And then we can see that all the simulations, and also CaPA and DMET, produce more precipitation than what SPADE has measured. Most of the type of precipitation here at Nipika was rain. So there's basically an overestimation of the precipitation at Nipika. And we also found that it was really dry at that time. At Power Line, which is at Fortress Mountain on the eastern side of the Continental Divide, we see that DMET estimate less precipitation than SPADE. And also, again, not DMET, but CaPA. And then all of the simulations overestimate. So I tried to divide it in color coding so you can see it more easily, but the 2-step have a red pinkish color, and then the 3-step has a blue color. And you can see that for Power Line, it looks quite good. Like if we see that the dash line, especially the experiment 6, it's quite comparable to the SPADE data. So we seem to capture a lot of the precipitation events. And then, so what we did is we wanted to compare, to evaluate the simulation, and also evaluate the satellite product where the correlation here is used as the spatial correlation. So note here that this is only for a 2-month period compared to what I've shown before, where it was for a 6-year period. So we see a slightly different result where the GS map is not here, for example, in the list of satellite that we chose to show you because it didn't show really good result at this time of the year. We're trying to understand why. So in the simulation, the GEM simulation, those are the circles here. The reference is the star, and the triangles are the satellite product. So we can see the 3 steps here, the black, the magenta, and the cyan are the 3 steps. And we can see that the cyan is the 3-step with class and forced by macrophysics as the best correlation, the best RMST, and also one of the best standard deviation, even if they're all really close. Then we can see also that the MS Web, that the performance is quite good. So we think that we could probably use those satellite information to evaluate the model. So now we will continue these activities by, so I think now we will use this cascade approach where we go from 30 kilometers and 12 kilometers, we use the microphysics to 3 kilometers. And we also are planning to merge our effort with other projects that we have at UQAM, where we do some simulation over Eastern Canada. And so we will use the Cordex domain over North America as the first one for 12 kilometers. And then we will cascade to 3. And I hope that we'll be able to do a 1 kilometer resolution simulation to be able to better capture the precipitation pattern over the mountains. The satellite data will be used as other set of data like CaPA and station data to evaluate the model. And we're hoping to be able to do 1-year simulation very soon, and maybe do a multiple-year simulation by the end of next year. So then if I continue with the regional climate modeling, all the effort that is done with WRF, with the WRF model, this is mainly led by Yang Ping's group. And also, so some of the activities is led by Yang Ping's group, most of it. But what I mean here is that the collaboration, we have a strong collaboration with the NCAR team, especially for the CONUS 1 and the CONUS 2 simulation. In particular, Roy Rasmussen, Chanhai Liu, and Kyoko Ikeda. So those simulations are done with a different model. And then also on different domains. So there's a 13-year simulation, as you know, that is available over Western Canada. There's also a 13-year simulation in the past, and PGW as Western Canada that is available, the green domain over the US, but also up to around, I think it's 65 degrees, so middle of Canada. And then there's a current major effort with the CONUS 2 simulations. So as you know, the first 2 databases are available. If you want to use them, you can contact us and we can direct you to the database. So there's the Western Canada database that is a 13-year from 2000 to 2013, and the CONUS 1, which is a bigger domain that is also 13-year. And those 2 types of data sets, as I mentioned at the beginning, have the historical simulation forced by reanalysis, but also PGW. So it gives you information on the the changes to the thermodynamic feedback. So this is not a climate projection simulation, but it is it gives you information on the changes in, for example, precipitation patterns in warmer and moisture conditions. So the CONUS 2 simulation is different than the CONUS 1. First, the domain is bigger, as I shown. I will go back, as I've shown here by the purple domain. So you can see that it covers all the US, almost all Canada. There's maybe St. John's here is missing, but up to north of Yukon. So it covers the entire, almost entirely North America. And this is a big effort where, like I said, that NCAR is leading, and Yangping's group are highly involved into it, where Lin Tao and Lucia worked on testing the 4-kilometer and running the 12-kilometer simulations, because with the 4-kilometer resolution, there's also a 12-kilometer run that is available. And then Lucia Zendua and Faye are working on post-processing the data, making sure the data from the historical simulation, for now they're ready, are available on Compute Canada and stored properly, and also on synthesizing the information for communication and sharing. So there's multiple steps that needed to be done to do the CONUS 2 simulation, the simulation design, the parameterization, improvement, choose the domain, the spatial resolution, and also how to deal with all the data that will be produced. And then there's some testing experiment that needed to be done with the land surface parameterization. Some effort was put on the groundwater, including the cloud fraction scheme as well. That predicts the cloud fraction within a grid point, and also different convection scheme and aerosols. And once this is done, then there's the simulation needs to be done. So to do that, there's forcing data needs to be prepared. And then once this is done, the data needs to be post-processed. So this is an example of a simulation for 20 years, but only for the month of January. This is the observations, but these are example of one of the 3 of the 13 simulations that were done. So we can see some differences with the observations in those 3 runs, but we can see some difference among the runs as well. Well, this one seems to be drier, for example, over Florida. This one, those 2 are more wet. And then the model didn't capture this maximum also in precipitation. So there are also some differences in the simulation, even if the same model is used, but in this case, different parameterization were used. This is the simulation design. If you're interested into the details, the version of WRF that is used, and then we can see it well here from the Earth. The domain that is used over North America, 4-kilometer, 12-kilometer, the surface output are available every 1 hour. And then, so the schemes, the New Thomson and the Meyer scheme is used, NOAA-MP is used, and then those different schemes that are used. And then the forcing data is something important. So what I mentioned before, this is a climate projection. So the 20 years that is done is it's a climate simulation. So it's forced by bias corrected climate model. So it's not forced by error interim. So in this simulation, for example, you won't find a specific event like we could do with the CONUS 1 or the Western Canada one. So the simulation is from 1995 to 2015, and it's run at 4-kilometer. If you're interested to know more about the forcing data, there's a paper from Aigo Dai in climate dynamics. And then for the future, there's 20 years at the end of the century. So this is, again, this is not a PGW, this is a climate simulation for 20 years. And then this is also at 4-kilometer resolution. So the perturbation, CCSM perturbation is used in the future, and also these two terms also used in the historical data. So you're probably curious to know what are the variables that are outputted. So there's a series 184 variables in 2D that are available every hour. And then every 3 hours, 26 variables. So we have also the entire atmosphere, temperature, humidity, wind speed, air pressure, and also mixing ratios of precipitation. There's also extreme variables from WRF that is outputted. And those data are post-processed. So they're post-processed for daily and 2-dimension and monthly as well. So depending of what you need, these are the different options. So just to give you an idea of the amount of data that it represents. So we have here, the CONUS 2 will require around 600 terabytes on Compute Canada, if I understood correctly. So there's the 4-kilometer that is around 250 just for the historical run. And then the 12-kilometer is, well, only a fraction, but still 30 terabyte with the data, hourly data being compressed. And then you just have an idea here what is the challenges here in using this big database. And in terms of storage, but also in terms of the manipulation of the data. As a comparison, Western Canada needed 150 terabytes and the CONUS 1 around 400 terabytes. So Yang Ping and her group provided me some initial analysis of the CONUS 2 simulations. And this is an example of the 2-meter temperature compared to the WFDI reanalysis. So that's a good news. It captured the main spatial incisional feature. When there's a cold bias over the prairies in Western Canada, the cold bias over the prairies is been attenuated. That was present in the CONUS 1 and the Western Canada simulation. Relatively warm bias in the spring. So we have the spring here. So we see there's a warm bias in the spring over the north. Oops. And then a cold bias over the winter, over almost the entire continent. Summer and fall biases are small, with a warm bias in the west and a cold bias in the east. So we have the fall here on this row and the summer. Then if we look at the the precipitation, it captures also the main characteristics if we compare with CaPA. So this is also provided by Yang Ping's group. So there's a wet bias over southeastern US during the summer. There's a wet bias along the coast of BC also throughout the season. And but overall, there's a good simulated precipitation over Western Canada and overall in the prairies. They have also started to calculate the annual cycle of temperature and precipitation over the Saskatchewan River Basin and the Mackenzie River Basin. And the CONUS 2 generally capture the main annual cycle in temperature, but in both cases, there's a cold bias in the winter, and there's a small warm bias in the spring and also in the summer. In terms of precipitation as well, it's also good. There's a small change in time here in the peak, but the capture and the main feature in both basins. The WRF underestimate the precipitation in both regions late in the summer and early in the fall, so around this time. And there's a small wet bias in the Mackenzie River Basin and a dry bias over the Saskatchewan River Basin, moderate wet bias in the Mackenzie River Basin in May and June here. So that gives you an idea of where we're at with the CONUS simulation. As I said, the CONUS 2 simulation historical are now completed. We're working with the computer science team and the data team to facilitate the use of the data by the GWF community. I invite you to contact us if you're interested into using the data. And also the future climate simulations should be available in the spring 2022. So now that we're preparing the historical simulation, we should be ready to proceed quickly with the future simulations so you can use them hopefully next year. So in summary, I presented to you the research activities that has been done in the Spatial Meteorological Forcing Data team. And then I try again to summarize this into different bubbles that are easy to follow, where we have a set of historical observational data and model data, and also a set of data for climate studies. The PGW simulations and also climate projections. There's the database developed by Gauchin, the evaluation of the remote sensing, and for the model data, the Western Canada, CONUS 1, and the GEN simulations. Those two are needed to do the evaluation. We need the observations to evaluate the model, to do the virus correction as well. And then these two types of approach here can be used also to do climate studies. And in the next step, we continue conducting those regional climate simulations and developing the targeted data sets. We work with the GWF core modeling teams to test and use those various data sets. And also we need to link with the other projects that would like to use the data set produced in the core modeling. So thank you very much for your attention today.
Excellent. Thank you very much, Julie. We are right on time at almost 45 minutes. Really good presentation. I learned a lot. Not being in this field myself, and very good overview of what's going on in the spatial meteorological forcing theme. So that was very helpful for me, and I think for attendees. So we can move to the question. Let me check if there are questions. If there are hands up. Don't see any. Yeah, so while waiting for question, I have actually a question myself. I was fascinated by the, basically this is the more scientific question. I was fascinated by the basically the result you show while perturbing the parameters of the model for the I don't know which product was that, but basically there was 13 parameter which it was perturbed, and then the result was different. Was it WRF or
in which part?
I think maybe you can. Unfortunately, I don't remember this slide, but
maybe it's at the beginning and.
Yeah, this one about yeah, here, right here.
Oh yes.
Yeah. So yeah, about 13. Yes. So is there any understanding of like the real impact of the parameters that they go into these models such as an uncertainty analysis on the output that we usually take as granted, like a fixed value and use? Or is it basically the edge of science that you are exploring?
So we know that there will be a different answer if you use a different parameterization, just sometimes just by changing the order in which the different processes are put in the model, that can change the answer. Sometimes a lot, sometimes not a lot. Like you see here some difference, small differences. And so if you use different convective parameterization, maybe the convection is initiated at different times and produce a different amount of the cloud information is different, and the precept is different. So and then this is all linked. So then the thermodynamic, the dynamics is affected. So there's a lot of research done and a lot of intercomparison to among scheme and models that are done. And I think this was an essential step to do. And then after it's compared and evaluated against observations to try to use the best parameterization for one thing, but also a combination of parameterization.
Yeah. So I'm asking this question because, like, when we run land surface model, just a small change in often fixed values like interception can basically change the whole transpiration. Or if we have a, let's say, let the roots get to some deeper moisture reservoir, it can basically change the result significantly. So that's very interesting to see.
Yeah.
Excellent. Thank you very much. And we have questions here coming from Chris Marsh. He's asking, I'm wondering if wind speed is one of the outputs for the future scenarios at 1 hour. I only saw 3 component winds in the 3-hour output. Oh, sorry, wind direction.
Wind direction. Yes, so if we well, I think so. We need to confirm with Yangping, but I would assume so because it's a standard variable that we would use. Wind speed. So it's a wind speed in the 2 direction, U and V, and then you can diagnose the direction of it. So there's the wind speed, the 2 components that are output. So yes.
Yeah. So he says, okay, great. Thank you. So another question from Andre Bertoncini, if I pronounced the last name correctly, sorry if I mispronounce it. Thank you for the great talk, Julie. For the satellite products that use gauge for calibration, was there any mechanism to ensure that gauges that were used for calibration were not used in evaluation? So basically, I think the question
That's a really good question. Yeah. So this is something we need to think about more carefully. And I think it's a similar issue of comparing CaPA, where CaPA used some of those gauges that we use also for the evaluation. So this is a good question, and we need to also dig more into which gauge are used for with the satellite product, and how is it QC'd? Because yeah, like Gao Chen said, I think Gao Chen put a comment here.
Mm-hmm. Yeah, I can read that. Thank you for the presentation. Yes. Yeah. MSWEP precipitation is used in several studies. MSWEP combines many satellite reanalysis and ground observation dataset. I think it's good. I think its good performance is mainly because of use of ground data. The role of satellite data could be relatively weak in high latitude region. What's your opinion about how to use satellite data? Just a second, what's your opinion about how to use satellite data or model data better in high latitude regions? Sorry, I just thought that maybe it's related to the Andrew's question. I don't know if you finished answering Andrew's question, but
yeah.
yeah.
And Andre, we can discuss more about this for sure. And Gauchin, this is a good question as well. And I think we should discuss this more to at our next meeting that we will have probably before Christmas. But I think that adding the satellite product, well, comparing it to the gauge, I agree. You know, when we compare to it, the MS web gives the better results, and that's the only product that used the 24-hour precipitation in it. So it makes sense that it gives better results. And we discussed it too at a meeting a couple months ago about this. So I think that adding the satellite product just add another perspective, another set of data to evaluate your model. So it may not be the best, but I think it adds another set of data that is not often used to evaluate model. Is it better? I don't know. We just started, so we'll see.
Mm-hmm. Yeah, so next question from Mohammed El-Shami is that basically a concern from people use land surface models. Apart from WRF Kronos 2, the developed data set are lacking some necessary variables to force land surface model, wind speed, well, direction and radiation. How are we going to use the developed data set? Example, CMIP6.
That's a good question. Maybe about CMIP6 in particular, we could discuss with Simon, is the expert with CMIP6. In terms of the Kronos 2, like you say, apart from Kronos 2, I think Kronos 2 will have the information that you will need. For CMIP6, I don't know. That's a good question. And maybe you can email it to me, and then we can connect with Simon and discuss this.
Yeah, bias corrected CMIP6 or EC errors, etc. Yeah, that's a good question. I can just add to that that there are packages or methods, as you know, which can derive those 7 variables for the land surface model from basically other variables that are available in the data sets with lower number of variables, like probably CMIP6, such as precipitation, Tmin, Tmax, and maybe, I don't know, some of them has been, some of them they don't have been, I'm not sure. So it goes maybe back to a modeling decision as well. If the modeler wants to use one of those packages to convert some of this data set to what can be used in the land surface model. Yeah, this can be a good discussion. Perhaps part of Mohammed Al-Shami question can also be answered in the team for the current generation modeling. That's, I think, also a good place to discuss it. I don't know if we answered Mohammed's question, but it's something to discuss.
I see that Bruce Davison has a related question to this in the question and answer.
I don't see. Do you see, like?
It's another window.
Okay, well.
Would you like me to read it?
Yes, please, because it's, yeah.
So Bruce said, thank you very much, Julie. There's a lot of great work taking place. As with Mohammed's question, will the team be producing bias correcting forcing fields with a variety of the CMIP6 model, past and future, for more than temperature and precipitation? So that's, I think that that is a really good question, and we will discuss this with Simon and see what's the future plan in terms of those variables.
Yeah, so Guccian also answered here. Thank you,
Oh,
Bruce.
yeah.
Yeah, sending this. I don't know where it was that I didn't see, but thank you, Bruce, for copy pasting it here. For EMRs, we do have a plan to, that's what Guccian is saying. For EMRs, we do have a plan to infer other variables to support land surface modeling. Packages like MetSim could be a choice. This may need more effort in the future. Yeah, that's what I was alluding to. It's a modeling decision if we want to use those packages or not. Yeah.
Yeah.
Yeah. So any other question or comment? We are getting close to the hour. So I would like to thank the participants and thank you, Julie, for this very nice webinar. This webinar is recorded and it will be uploaded in GWF YouTube channel. I just want to say that the next webinar for core modeling activity will be on December 2nd. John Pomeroy will present on the next gen modeling activity in the core modeling theme. There is another. Okay, yeah, thank you, Curtis. Yeah, so thank you very much and see you in the next webinar. Have a nice rest of the day. Bye.
Bye-bye. Thank you all.